All right. We're going to pick back up talking about torque and rotational statics for my Physics C kids. I just finished recording some Physics 1 videos, so I'm kind of excited to get back to some hardcore physics. Okay, we're talking about rotational statics and torque. Okay. Um, okay, so let's first define force conceptually as what causes an object's center of mass, or cm, to change translational motion. Okay? So, therefore, let's define torque as being what causes an object's, an object to change, not objects, an object to change its rotational motion. Okay, so to get something to start spinning or to get something to start rotating, okay, then you need a torque to act upon it. Okay, um, the equation, if you took Physics 1 with me last year, or really in Physics 1 last year, you probably learned the general equation, which was RF sine theta. That's actually not the most proper equation. The most proper equation is that it's actually a cross product of the vectors for R and force. Okay, the R and force vectors, which then, of course, does become the traditional equation that we all know and love, RF sine theta. Okay, and then um, and then the another way to write this, and honestly, I would suggest that you just keep writing it like this instead of doing it the way that I'm about to show you, is torque is equal to R perpendicular F. Okay, what component of R is perpendicular to F? You could also do what component of force is perpendicular to R. Doesn't really matter. They're going to get you the same thing anyway. Okay, but RF sine theta just bakes it all into one step, and it's usually easier to do. Okay. R is the distance from the axis where force is applied. So I can say R is distance from axis where force is applied. I'm just gonna call force applied. Where I'm just gonna call force F for shorthand, and then theta is the angle, okay, between R and F. Okay. Okay. So you see all that stuff there. Now understand, right, that your force has two components relative to R. There's the component that's perpendicular to R, or sorry, parallel to R. Okay, this is the force that's parallel, and this is the force that's perpendicular. And if you remember last year, I taught you that anything that acts directly pointing towards or directly pointing away from the axis point does not apply any torque to any sort of lever arm or anything like that. So, for example, this parallel component of force is not going to do anything to the axis. The perpendicular component of force is going to be the only thing that actually applies a torque onto the lever arm. Okay. Okay, this was originally an Indiana Jones problem. I rewrote it though to talk about myself, because why not? While out on the town, Mr. Mitchell encounters a 150 kilogram, 10-meter long plank, lies flat on the cliff edge where 3.5 meters of the plank are over the edge of the cliff. As shown, I am 100 kilograms and I walk out onto the plank to retrieve a love letter from Karen. How far can Mr. Mitchell go from the edge of the cliff before the plank tips over? Okay, well, that is a great question. Well, first we need to set up, okay, a balanced torques equation. That's going to be the best way to approach this. Is I'm going to set up so any clockwise torques need to be equal to any counterclockwise torques. Okay. Okay. And I need to first figure out what torques are acting. So first off, I should have. Well, I mean, where Mr. Mitchell's standing, right? That's me. Okay. I've got little. I'm going to call this little mg. Okay. I've got the center of mass of the plank is also technically going to apply a torque, because right here is our pivot point. Okay, there's our pivot point right there. I'm going to draw a little caret beneath it. Okay, so that you know that that's my pivot point. Okay, like a seesaw maybe. Okay, the center of mass should be, or sorry, the mg of the plank should act from the center of mass. So let's see, 1, 2, 3, 4, 5. So that's going to be right about right here. Okay, I'm going to call this capital Mg. And then there is a normal force protruding from here, but that's actually not going to apply any torque because it's pointing directly away from the pivot point. Okay? So all I got to do is set my clockwise torque. So what's going to cause my plank to rotate clockwise. Okay, that's going to be little mg for Mr. Mitchell. Mg, how far out am I? I'm a distance x. Okay. And then my counterclockwise torque is just the capital Mg right here. So this is going to be capital M G, okay? And the distance from here is approximately 1/2 1. So about 1.5 distance, or 1.5 meters, okay? Okay, because each line on here is 1 meter. So then I can plug all my values in, okay? Little mgx, that's going to be 100 times 10. X, we don't know. Okay. Big M is, where is it? 150. Okay. G is 10. And then this is 1.5. Okay. Okay, so I calculate the whole thing out. I end up getting 1,000 x equals, this ends up being 1,500 times that. I should end up getting about what am I thinking right now? Oh, sorry. Actually, what I did in my key here was I actually knocked out the tens here, so that actually this just becomes 100. Okay, so it's 100x equals 225. Okay, and then you can figure out from there that x should be equal to about 2.25 meters. And if you actually check on the page right here, it's half 1 2 ish. Maybe he's getting close to there. Okay. Okay. So there's that. Okay, 2.25 meters. Okay. Oh wait, 2.25. That's actually right about where he is because he's a little off center from there. Okay. It's about exactly 2.5 or 2.25 meters. Okay. Okay. That's the first torque problem. Okay. Let's look at the next one. This is a bridge that is suspended from two ropes. So this is like the a bridge problem. Okay. And the big difference here is that you have a couple more torques. So you have, sorry, you have tension in the left cord right here, okay, pulling up. You have tension in the right cord here, pulling up, okay. You have mg from the center, so 1, 2, 3, 4, 5, okay. I'm going to call that big mg, sorry, because that's the plank. And then you do have mg from where Mr. Mitchell is, okay. Now, the first solution, okay, or actually, it's kind of a multi-step problem here. The first problem is torque, or so the first thing I need to do is use torque. Okay, so if I'm using torque, I'm going to use that the clockwise torque needs to be equal to the counterclockwise torque because the bridge isn't rotating at all, right? Well, what I need to do when I do this is I actually need to pick a pivot point, okay? And I can pick any point really on here that I want, but it's going to be way easier if I pick one of the ends, okay? And I'm actually going to do right here, okay? My pivot point being the right side of the bridge. So then you'll notice that these two torques are going to cause the bridge to tip. These two are going to cause the bridge to tip counterclockwise. This one's going to cause the bridge to tip clockwise, okay? So let's see. So if I do my clockwise torques, that's just going to be T sub L, which is a distance 10 meters away from the pivot point. Okay. Capital Mg, which is a distance 5 meters from the pivot point. Okay. And then I add to that Mr. Mitchell's Mg, and he's only 2 meters from the pivot point here. And I know on the left side it says he's 8 meters from there, so I guess maybe it could be easier to do the left-hand side because you're given more numbers, but it's not that hard to figure out, really. Okay. And then if I plug in all my numbers here, I can figure out what the tension in the left cord is, because this is going to be TL times 10 is equal to, okay, this is 150, 1,500, okay, 1,500 times 5 plus he's still 100 times 10 is 1,000. okay, times 2, okay. And this ends up being TL, times 10 is equal to 7,500 plus 2,000, okay. And this gives you about 95,000, which you divide by 10, you get about 950. So you should get 900 and I'm just going to draw an arrow here. You should get about 950 newtons for TL. Okay, TL is 950 newtons. Okay, and then the second part is that you actually then have to use Newton's second law. Okay, so when you're using Newton's second law, use N2L. I'm going to call that N2L. Okay. When you use Newton's second law, you're just going to do the up forces, okay, equals the down forces. Okay. So my up forces is tension L, TR, and then I need to set that equal to mg. Okay. So this is going to be TL plus TR equals capital Mg plus little mg. Okay. And now all I got to do is just plug everything in here. Okay, so TL, all right. TL we already solved earlier is 950. So 950 plus TR, which I don't know yet, equals, this is going to be 1500 plus 1000. So I get 950 plus TR equals 2500. Okay. And if you subtract the 950 from both sides, you should end up seeing that the tension in the right cord is going to end up being about 1550 newtons. Okay. Okay. Example number 3, this is called the leaning ladder problem. It is a challenging problem that we look at in physics because it is a multi-part problem in where you have to kind of piece together a lot of stuff. So you have a uniform ladder of mass m, length L, propped against a wall so that it makes an angle theta. The contact between the ladder and the wall is frictionless, but the contact between the ladder and the floor has a coefficient of friction mu. Find the minimum value of mu such that the ladder will not slide. Okay, so when you do this, okay, there's a whole bunch of forces acting on it at any given time. You've got normal force from the floor. Okay, I'm gonna call it F sub NF. Okay, you've got friction from the floor. Okay, I'm gonna call that F sub FF. Okay, you've got the center of mass mg. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. Okay. I'm gonna call that. Let's call that little mg. Okay. And then you've got at the contact with the wall, you do have normal force. Okay, normal force from the wall. Okay. Okay, and you have to do a whole bunch of stuff here. Okay, you have to do a lot of stuff. We need to first use balanced forces. Okay, let's use balanced. Let's set up Newton's second law for forces. This is left. My left forces need to be equal to my right forces because if the ladders at equilibrium, then they should be equal to each other, right? Okay, well, what force points to the left? That's going to be the normal force of the wall. Okay, and that should just be straight up equal to the force of friction from the floor. Okay. Okay, I can't really do anything more with that, but I can keep making Newton's second law equations. If I do my up forces, okay, equal to my down forces, okay. Well, my up forces is the normal force of the floor, okay, and my down forces are just mg, okay. The final part is that I have to write a balanced torques equation. This is actually where things get a little bit more complicated, okay. So what I'm going to do is I'm going to pick a good pivot point, and that pivot point, or that axis, I'm going to make just right here at the floor, okay? This is my axis right here. I'm going to make that my axis because that makes my life easier. I can actually knock out these two forces. If I do it on the wall, I can only knock out one force, okay? And you don't really want to do that. Okay. So when I do this, okay, when I decide to pivot it about the floor, okay, which makes it easier on me, I have to consider my clockwise forces and my counterclockwise. Mg is going to cause it to swing down. Normal force would cause it to swing this way. So clockwise would be normal or Mg, and then normal force would be counterclockwise. So I would have to do the distance. So I'd have to do again that force. I would have to do RF sine theta, right? So I would say that this right here is half the length. Okay, so I can do 1/2 L. Okay, that's R F mg. Okay, mg sine theta. Okay, and that makes sense because this component right here should be theta, right? Okay, now I set that equal to, again, RF. This is a whole length L away. Okay, so there's R. F is F normal with the wall. I don't know what that is, but then I need to do sine theta. Wait, here's the thing. This angle right here is theta, okay? But this angle right here is not theta. But what I do know, okay, what I do know is that theta and this angle right here, I'm going to call this phi, okay? Angle theta and phi together have to make 90 because this is going to make a perpendicular angle right here, okay? They have to make 90 degrees in total, okay? So when I do that, I have to recognize that theta plus phi, okay, theta plus phi equals 90 degrees, okay? Well, I can make a right triangle here, okay? And when I make that right triangle right here, I know that this angle has to be 90, okay? Hey, wait a minute. And so the remaining angles in here have to add up to 90, right? So the 90 here, and then these two have to add up to 90. Wait. But then that means that phi plus something equals 90. Oh, so this angle right here is actually theta. Okay? That angle in the top corner is actually theta. So normal force of the wall is actually, it's actually just this perpendicular component is going to be cosine. Okay? This part's going to be the cosine component. Okay? So I can actually express this in terms of theta if I make it cosine theta instead of sine. Okay? I could do it in terms of phi if I wanted to, but we don't want to have two different angles, especially when you don't have values for those angles. Okay? Okay, now I'm going to actually start with the Torx equation and work backwards because it's the easiest way to do it. The Torx equation is the easiest one to do because what I'm going to do is I'm going to figure out what the normal force of the wall is going to be. Okay? And that's actually not that bad to do because I just need to divide both sides by L cosine theta. If I divide both sides by L cosine theta, I end up getting the normal force of the wall would be equal to 1/2 L mg sine theta over L cosine theta. And one thing that you should notice is that your L's will cancel out, and then you have sine theta over cosine theta, which turns into tangent theta. Okay? So then I would get the normal force of the wall would be equal to just 1/2 mg tangent theta. Okay? Okay, cool. Cool. Here's what I'm going to do. I'm going to take this expression, okay? I'm going to take this expression that I just wrote, and I'm going to plug it in for up here. Sorry, I meant to circle the W too. Sorry, messed up. Okay? So I'm just going to port that down here. Okay? Really quickly, the force of friction with the floor, okay, the force of friction on the floor should be equal to mu times normal force of the floor. Okay? Well, I know that the normal force of the floor should just be mg, right? So then I can actually just say that the force of friction on the floor is equal to mu mg, right? And that makes things really easy, so we don't have to worry too much about it, right? That's pretty cool. Okay. So I can take this expression and plug it in for that too. So I can actually make a bunch of substitutions right now to make this a lot easier. This will become 1/2 mg tangent theta. Okay. This will become mu mg. Okay. And you should notice that you have mg on both sides of this equation, which means we can cancel those out. And you end up getting an expression for mu, which is 1/2 tangent theta. Okay? I think when I lectured on this in class, I actually did like extra steps to kind of show more steps, but I think this gets you the point enough. Okay, this gets you enough of the point. Okay, and then this is the final example for this section is over a guy named Crangus McBasketball, which is an Impractical Jokers reference. Okay, you can see I'm wearing the Impractical Jokers are on this shirt. Okay, Crangus McBasketball. He's a character that was like in Impractical Jokers for a minute. It was kind of silly. Okay, I mean, not even a character. It was a fake name that was given. Um, Now, when you have a person on the ladder, things do get a little bit different, and it actually does kind of get more complicated. My forces are fundamentally the same, except for now that I have Crangus McBasketball on there. Still have normal force of the floor. Still have the friction force of the floor. I still have one, two, three, four. I still have mg of the ladder. I now have Crangus McBasketball, who I'm going to call Big M. Okay. Um, Normal force of the wall. Okay. Okay. That's a lot of forces, right? That's a lot of forces, okay? Now, when you do this, okay, we're assuming that the coefficient of friction mu is the minimum found above. So with that information, I can actually write a new expression for the force of friction from the floor, okay, which we found earlier to be mu mg. But now, if I'm going to replace that mu from earlier, it's actually going to be 1/2 tangent theta mg, okay? I don't like putting stuff on the other side of the theta. I didn't really think too much when I wrote that, okay? So again, I'm going to rewrite my Newton's second law, okay? Left forces equal right, okay? Well, my left forces are simply still normal force of the wall, and that needs to be set equal to the force of friction on the floor, okay? Okay, my up and my down forces, okay? Up forces equal down forces. Okay, same thing. My up forces it's just the normal force of the floor, really. Okay. And set that equal to the both mg's. Mg plus capital M G. Okay. And then again, I have to do my torques again. Okay. Oh, sorry, not plus, equals, okay? It looks like I'm saying like not equal to, but it's equals to, okay? Now all I gotta do is I have to actually account for Crangus McBasketball, who's going to go the same direction as mg. So this is really going to turn into 1/2 L mg sine theta. Okay, plus I need to account for him, who's up some distance x. I don't know what the x is. X mg sine theta. Okay, and then the normal force is unchanged. Okay, equals the normal force, which is just going to be L uh, normal force of the wall. Okay, cosine theta. Okay, just like we saw last time. Okay, well, what I'm actually going to start with is I'm actually going to start on the left side now. Okay, and I am going to make this substitution. Okay, I'm going to say that the normal force of the wall has to be equal to 1/2. Let's see, force so force of the normal force of the wall, or sorry, normal force of the wall equals the force of friction from the floor. Okay. Um, Oh, I wrote it backward. I wrote it backwards in my key here. So then the force of normal force of the wall is still untouched. This is going to end up being 1/2 tangent theta. Okay. And then actually I wrote mg here, but it really should be normal force from the wall, normal force from the floor. Okay. F sub nf. Okay. So it should be F sub nf. Okay. Okay. Then I can make a substitution that f sub nf is this value, is this up here. So what I'm going to do is I'm going to take the f sub nf and I'm going to do replace that in there, okay? And yes, this is going to become a really weird looking kind of equation. F subnormal of the wall would be equal to 1/2 tangent theta, okay? Mg plus big Mg, okay? And then, yeah, equals normal force of the wall, okay? Now, here's the part that's really, really weird, okay? This is the part where things get, like, really wonky. Is as now I have an expression for normal force of the wall, so what I'm going to do is I'm going to take this, and I'm going to plug it in for the normal force of the wall that I got up here, okay? And that's going to be, oh, that's gonna make a huge mess, okay? It's going to make a huge, huge mess here, okay? Absolutely crazy, okay? Um, But let me move this down just a little bit so I have a little bit more space to write. When I do that, it's going to end up giving me this really long equation: 1/2 L mg sine theta plus x mg sine theta equals L. Okay, and then I plug this whole thing in: 1/2 tangent theta mg plus capital M G cosine theta. Oh my gosh. And you're like, now you have a headache because it's like, why am I doing all this stuff? But let me tell you this, okay? Let me let you in on a little secret here, okay? If you recognize, okay, that tangent theta is sine over cosine, you can make your life so much easier, okay? Because what you can do is, if you know that tangent theta is equal to sine over cosine, then you can recognize that cosine theta will cancel out with the cosine theta right here, and then when you divide sine on both sides, it cancels out those signs. We can eliminate all of our trig functions in one fell swoop, okay? And that's exactly what I'm going to do because I do not like using trig functions, okay? Okay, so I get 1/2 L mg plus x mg equals L 1/2 um, mg plus capital M g. Okay, and I need to distribute this part too, so this is going to be kind of a mess. So it's 1/2 L mg plus x mg equals 1/2 LMG, 1/2 L little mg plus 1/2 L big M G. Okay. Oh, you're like, I'm tired, Mr. Mitchell. I want to go home. Yeah, me too. Okay. But if you take a look at this, right? Okay, you actually can cancel out a lot because if you subtract 1/2 LMG from both sides, you can knock out this part. Boom, boom, done. Okay. And then you're left with xmg equals 1/2 L capital MG. Okay. And this, I'm so sorry, I wrote it wrong here. This should actually be capital MG as well. I didn't really make it clear. Okay. But since you have capital MG on both these terms, you can then eliminate them. And you should end up finding that x is just going to be equal to 1/2 the length of the ladder. Okay. Okay. That is all of the torque. Okay. So we'll be back next time with some Atwood machine stuff. Okay. Have fun.